Hello, it's Mr. Waters back, and we're going to continue where we left off with the PowerPoint video. We are on the brink of actually solving a specific related rates problem. Now we're going to start out with kind of a stripped down, abstract looking one. Okay, on the top of my page here, this has got all of the steps and the information that you saw in the video, in the PowerPoint, I mean, and then this is, I'm going to download this as part of your notes, of course. Now I'm going to slide this up here, and we're going to take a look at this problem here, which I've started to write out a little bit. Okay, here's the example we're going to do. Suppose x and y are both differentiable functions of t and are related by the equation x squared minus 3x. They want us to calculate or find dy dt, in other words y primed, when x is equal to 3, given that dx dt is equal to 2. In other words, given that x primed is equal to 2. Now we're going to use implicit differentiation here in order to actually take the derivative. We'll get to that in a minute. But the point is something you've got to see is that x, or rather y, is not a function of x. And x is not a function of itself, like our previous problems. They're both changing quantities with respect to t, which will be time usually for us. So it's like the snowball problem, okay? The snowball is melting on the counter, and both the volume and the radius are both functions of t. Now we could write the volume. There's a volume formula that relates, you know, the volume is equal to, tells you what, you can calculate the volume of the snowball given the radius, but it's not a static quantity. Volume and radius are both changing with respect to time, so they're both functions. Okay? Now, so in this particular case, we don't need a picture because there's no picture involved with this problem. So we'll go straight to 2, in which we're reading the problem and we're identifying all quantities as find, when, and given. Okay? Find is the rate of change that you're trying to calculate. Every problem will say calculate or find or what is this rate of change, and that's what you're asking for. So in other words, the find is the variable, the quantity that you're solving for, which will always be a rate of change. Now, you're also going to be given another related rate of change, right? The radius, the change of the radius as in relation, the change of the radius in the snowball problem, right? And so in this case, we're told that x primed is equal to 2. And then because the quantity is changing, we're going to be told we want to solve when y prime. We want to solve what y prime is at the exact instant in time when x is equal to 3. X is not always equal to 3 because it's actually changing at a rate of 2 meters per second or something. But at some instant in time, x, as it happens, is exactly equal to 3 for an instant, and that's the point in time that we want to know y primed. Okay, so we got to write that all out fair and square. Then number 3, we have to specify an equation. And here, in this case, they gave it to us. Usually we've got to kind of figure out what it is. But in this case, they give us the equation that relates the quantities that we're working with, x and y, together all in one formula. We had to do the same thing for the optimization problems. Now, what's different now is that we're not interested in solving for y. We want to know y primed. So what we do is, step 4, we take the derivative of this using implicit differentiation and the chain rule. So remember the chain rule, that y is a function of t, so it's not just 1, it's whatever the derivative is. So wherever we see a y, that generates a y primed. Okay? And then here, notice here, then we take the derivative here, but keep in mind, this is not just going to be 2x, because x is not just a function of itself, it's a function of another variable t. So we have to use the chain rule here. We multiply the outside as x squared, so we multiply the 2 in front as usual, but then the derivative of the inside, the derivative of x, is not going to be 1, because x is a changing quantity. It's going to be x primed. In a similar way here, when we take the derivative of 3x, it's not just 3, it's 3 times the derivative of x, which we write as x primed. Okay, so that's different. So when we do our when we practice, when we use our implicit differentiation ideas, we're not only, whenever we take the derivative, we're not only going to generate a y primed, we're also going to generate an x primed. Okay? All right, so. Now that we've done that, now we take the values that we're given and we plunk them into the equation. Okay, and so step 5, substitute the resulting here. So we see here, I'm going to use the red pen here, we see here in the black pen, we see that x is equal to 3. So y primed is equal to 2 times 3. X primed was equal to 2. So the 2 goes there. Minus 3 times x primed was 2. Okay? So notice here, okay, look at that. X primed went there and went there. And then the value of x for the given time is there. So that's 12 minus 6. So y primed is equal to 6. And we don't have any units, but that could be like meters per second or kilograms per hour or whatever the rate of change is based on what these quantities are up here. Okay? So that's how that works. Okay, so now we're going to try another one. I'm going to put another one up here, and we're going to try that one. Okay, we're going to put that aside for a second. All right, so let's say we've got this one here. So this is going to be example 2, we're going to call it. Y is equal to 2x squared plus 7x plus 6, right? And we want to know, we want to solve for what is y primed when x equals 2 and x primed is equal to negative 4. Okay? So here's example 2, right? So now, again, not a picture for this one. We'll get to the picture ones. Okay? And so we're going to go straight to the find when given. Find when given. You've got to specify these because this is where you summarize the information that you're given to solve the problem and where you specify the quantity that you're solving for. Okay, well it says here, what is y primed? Okay, so I'm going to put that right here. We're finding y primed. And we want to know it, and as y is changing, x is also changing, and we're given, the other rate of change we're given is x prime. When we're solving for one rate of change, we're always going to be given another related rate of change. Okay? Okay, so when, and at what point in time, as x is changing, oh, and that's negative 4, isn't it? As x is changing at a rate of, I don't know, negative 4, meters per second or whatever it is, at the instant in time when x is equal to 2, that's what we want to know what y primed is. Okay? All right, good. So now, so that was step 2. Now step 3, we have to specify an equation that relates x and y, the two quantities we're working with here. Luckily, you've been given that. 2x squared plus 7x plus 6, right? Now, that's step 4. Now we take our slightly new style derivative where we're implicitly differentiating the x and the y and the x. Because why? They're both functions, and I didn't write it up there, but they're both functions of t, you understand. It's just that the variable t is implicit inside the equation, inside the function. Okay, so now we'll take the derivative. Okay, the derivative of y is y primed. Whenever we see a y, it's going to generate a y primed. We'll use the chain rule. Now, chain rule here, the derivative of the outside is 4x. The derivative of the inside is x primed. Okay? The derivative of the outside is just 7. The derivative of the inside is x primed. And the derivative of a constant is still 0. So the 6 still drops out. Now, that's step 4. This is the derivative function that's going to tell us our answer, that's going to give us the problem we're solving for, which is y primed, right? So now that we've got this derivative equation here, now we plunk our information in, okay? Ooh, and I see I've gone off the paper a little bit. Sorry about that. I'll zoom out a little bit. There we go. Okay, trying to make this as big as possible for you guys to see. Okay, so now this is going to be, so we take the 2 and we put it where the x is. Wherever we see an x, we're going to put the 2, and wherever you see an x prime, we're going to put the negative 4. So times negative 4 plus 7 times negative 4. Okay, so that's negative 32, and this is negative 28, so that's negative 60. So y primed, the rate at which y is changing, with respect to t is negative 60, like, I don't know, meters per second or something, depending on the units of the quantities. Does that make sense? Okay, now, if you please, you guys go ahead and please try this one. Okay, y is equal to 2x, negative 2x squared plus 3x minus 4, and we want to know what is y primed when x is equal to 3 and x primed is equal to 2. Okay, now I'm going to stop for a minute here, and you should put the video on pause. Go back on your own and work through the 2 problems you've already done if you need to, and please try this one on your own just to kind of test your skill now. And then once you've done that, you're going to come back and you are going to you'll check your work. You'll start the video again and check your work, okay? So right now, go ahead, hit pause. Okay, so you can see there that, oh look, okay, so that's how that one works, okay? Specified what, find, when, and given. Then I wrote out the equation that related x and y. Then we took the derivative. Keep in mind we used the chain rule there. That's not just 4x or negative 4x. It's going to be negative 4x x primed. And this isn't just going to be, 3. This is going to be 3 times x prime. The constant still works out to be a derivative of 0. And then once we've got that, we plug away. Okay, very good. Now, and that was example 3. Now there's example 4. We're not always going to solve for y primed. Sometimes we're going to solve for x primed. Okay, so for instance, let me put that aside there. Let's say we've got this equation here. Okay, let's say x squared plus y squared is equal to 7. Okay, all right, we want to know, find or calculate x primed, okay, when x is equal to 3, y is equal to 2, and given y primed is equal to negative 4. Okay? So I've given you an x and a y. In this case, you'll see y in a minute, given that y primed equals to 4. So here we want to find, so now okay, again, not a picture. We'll get to those in a bit. Okay? So let's see. So this is going to be, so find when given, we're supposed to find x primed, right? Because it says find x primed. We're given that y primed, oopsie, that's supposed to be given there. We're given that y primed is equal to negative 4, and we're given a couple of momentary values here. When x is equal to 2, and when x is equal to 3, and y is equal to 2, right? Now, so we have a relationship, x squared plus y squared is equal to 7, right? We take the derivative using a chain rule. And remember, both of these are functions with respect to t. So here, using the chain rule to get the outside, 2x, derivative of the inside is x primed. Chain rule to get the outside, 2y times the derivative of the inside is y primed is equal to 0, right? Because the derivative of the constant is still going to be equal to 0. So now, we want to find x primed. Well, there it is. So we can either take this equation and solve it for x primed and then substitute, or we can just go ahead and plunk the numbers in, right? We know that x is equal to 3, so that's going to be 2 times 3 times x primed, plus y is equal to 2, so I'm going to put that in, times y primed, which we're given, which is 4, and that's equal to 0, right? So that's 6x primed plus 2 times 2 is 4, times 4 is 16, is equal to 0. So x primed, I think you can see it's going to work out to be negative 16 over 6, or negative 8 over 3. Right? And again, that's a rate of change in feet per second, or, dollars per hour, or whatever it is the function we're working on. Does that make sense? Okay, I hope so. Okay, so now one more point, by the way. I'm going to go back, and I'm going to do this one again, except we're going to start with a slightly less amount of information. I'm going to tell you this. X squared plus y squared is equal to 7. Find x primed. And I'm going to tell you when x is equal to 3, given y primed is equal to negative 4. Uh-oh. Wow, up here, that should have been negative. Sorry, negative. I'm not going to go back and do it again. But that makes that negative 16, and so that's positive 16, right? Okay, good. So that's positive 8 over 3. Sorry. Okay. Here, x primed. Find x primed when x is equal to 3, given that y primed is equal to negative 4. Now this time, in this version of the solution, I'm not going to tell you what y is. So how are we going to know? Okay, so let's see here, let's proceed from given just this information here. So we still do find when given. Still looking for x primed. Now we're given when x is equal to exactly 3, and we're given that the other related rate is still negative 4, right? Okay. Well, cool. So we still are given that that's step 2. This is still step 3, right? So we still know that x squared plus y squared is equal to 7, right? Okay, well, okay, so now we take the derivative, which again works out to be 2x times x primed plus 2y times y primed is equal to 0. So now so that's step 4. So first off, you know, in the beginning it all looks the same, doesn't it? But here's the difference. We look over here and we go, x is equal to 3. So I'm going to put 3 in there, and x primed plus 2, and we think, uh-oh, wait a minute. We know that y primed is negative 4, but we haven't specified a momentary value for y. So we don't have anything to put there. That's okay. Kind of something that might happen when we get to this point is we might be able to look back we might have to look back and go, oh, wait a minute. We don't have enough in the when position here. We don't have enough to substitute back into the derivative equation here. So what are we going to do? At this point, well, we can solve using the original equation. We can solve what y would be when x is given, when x happens to be 3. So I'm going to put, so if we ever have to do this, see, here's what we're asking for. What would y have to be at that given moment when x is also equal to 3? So now we take this x and we put it back up there, and I'll put this in red. 3 squared plus y squared is equal to 7. Okay? So that's 3 squared is equal to 3 squared is equal to 9 plus y squared is equal to 7. And we see here that y squared is equal to negative 2, which is an uncomfortable value. I should have picked a better x, right? So this is negative 2. So y is going to be, and we're just going to go with it right now, the square root of negative 2, which is imaginary, but it doesn't change it for us. So now we know that y squared is square root of negative 2. Now we go ahead and we substitute that in. And now we put the y prime for negative 4 is equal to 0. Now, okay, so I should have started with a better value than 3 for x, but that's okay. Doesn't really matter because the process is the same. It's just that when we do this in future problems, these quantities will always come out to be real numbers. So that's 6x primed, and this is going to be, what is that? Negative 8i rad 2 is what we called that, right? Equals to 0. So x primed is going to be equal to 8i rad 2 over 6, and there's our related rate. Now the point of this is that sometimes in this step here, when we get to here, we're going to see that we're not given enough information, or rather we're not given complete information to substitute everything. So what we'll have to do is, using the original equation, go back and solve for, in this case we solved for what y would be when x is equal to 3, because we need 2 whens, not just 1. Okay? So up here, I actually told you what both x and y would be, but it turns out that, you know, as you can see, I only really needed to tell you the x, because once we've taken the derivative equation here, we can solve for y. Okay? All right, so that's enough of that. I'm going to put some practice problems on the board, on the camera here, and then we're going to have some homework problems for you to try out, and then we'll go at this next time, okay? Very good. And then you should try out the classwork problems, because I'm going to have all the solutions worked out before you try out the homework, okay? Bye.